Hi everyone, I'm Tal, and in this video we will talk about tips and tricks for efficient code execution on CPU and GPU with PyTorch. And the main goal we wish to achieve is an optimized code that runs faster by maximizing the utility of the GPU and allowing efficient transfer of data between the CPU and GPU. Okay, so let's start. Great. Okay. So we will provide tips and tricks for efficient code execution on CPU and GPU, and this is relevant to any project you work on. It's just a general good practices to work when you code with PyTorch. And we'll see a lot of tips here, and I hope that you'll find this useful in your project. Okay, so the first thing we want to understand is how can we monitor the utilization. So we have the CPU and the GPU, and both of them are working during the execution of our code, and we want to monitor and see what happens and what goes on when we train our models. So the simplest way to monitor the GPU utilization is running nvidia-smi from the command line, and you can also run this directly from a Jupyter notebook. And if you are interested in monitoring the CPU utilization, then in Linux, usually htop gets the job done. So keep that in mind. Now, if you want to go the distance and use a custom-made tool, then I recommend nvitop. nvitop will provide you with colorful monitoring UI. So if you want to use it, then you'll get a really nice monitoring app. But let's stick to the standards. So the first thing we do is nvidia-smi. Now nvidia-smi will output the current status of the GPU. Now if you're not working in a Jupyter notebook, then just run the terminal and write watch nvidia-smi, and this will be updated online. Okay. So here you just get a snapshot of the current status. Okay, and so let's try to understand what we see here. Okay, so following is a description of most of the fields here, just the important stuff, and you can read on about the rest of it in this notebook. But let's start with the important things. So in the top row, okay, so this one, we can see a couple of things. The first one is that the driver version. So the current version of the NVIDIA drivers that are installed on your machine. Okay, and this is important because it will determine the maximum CUDA version you can install. So CUDA version are the NVIDIA GPU's drivers to run tensor operations. Now, when you install PyTorch, then if you recall, then you need to install also the CUDA toolkit, and it has a version number. Now, the version you see here is not the version of the drivers that are installed, of the CUDA drivers that are installed, but the maximum CUDA drivers that the current NVIDIA driver supports. So with this driver, you can install CUDA toolkit up to 11.7. Okay. And this is important. If you want to see the actual CUDA drivers that are installed on your machine, then use nvcc-v, and this will print the current installed driver. So you can see here it's 10.2, even though the driver supports up to 11.7. Now you need to match the driver to the PyTorch version you're using, and you can see on the PyTorch website what is the latest supported drivers. Let's move on. So the second table, or the first one, depending where you start your counting from, then here we can see the number of GPUs we have on our machine, and here we have only a single GPU, so GPU number 0, right? And we can see some details about the current status of this GPU. So the first thing is the temperature, right? So here it's 40 degrees Celsius. Now, usually when you run your models and you're maximizing the utilization of your GPU, the normal operation temperature should be around 80 degrees Celsius. Now, if it goes above, then you should consider that there might be a problem with the cooling or some other hardware issue. So you don't want your GPU to overheat. It can cause all sorts of issues. The next thing is the performance, and basically we can see there are a couple of performance modes or performance states for the GPU, which range from P0 to P12, and it refers to the maximum minimum performance states of the GPU, right? Now, another important field is the memory usage. So it denotes the memory allocation of the GPU out of the total memory. Now, this should help you understand or balance your model size in batch size and other hyperparameters that greatly affect the memory required from the GPU. So this field right here, right? So right now we are running nothing. So we occupy 0 megabytes out of 4 gigabytes. Okay. And the final important field in this table is the GPU utilization, and this is what we mostly care about. And it indicates the percent of GPU utilization, that is the percent of time when kernels were using GPU over the sample period. Now, the sample period could be between 1 to 6th of a second, depending on the type of GPU. And in case of low percentage, then the GPU is underutilized. So that means that your code spends time on reading data from the disk or other stuff that are not related to training your model, right? So you want this to be high as possible, okay? So if you're seeing very low percentages, then either you have a really good GPU and you're training a very small model, or otherwise you are not utilizing it as much as you can. And we paid for it, so we want to use it as much as we can. Now the second table here, right at the bottom, it actually tells you what processes are utilizing the GPU. So this is good when working on servers and there are multiple people that are working, and you want to see who is occupying the GPU. Now in this case, we only have the notebook open, so we have a single process. You can see it's PID. Now, if something happens and you need to kill the training script, then this is the PID you can use for the kill command, right? Okay, and of course, if you have multiple GPUs, you will see which process runs on which GPU. Okay, cool. Now there are more parameters. You can use nvidia-smi --help to get an idea of what other things there are, but we covered the most important stuff. And you can also see, you can read about more of them here. Now, if you want to manually control the cooling of the GPU, so of course don't do it unless you know what you're doing, then there is a cool tool called Cool GPUs, and this will help you control the GPUs from the terminal, and just keep that in mind if you want some advanced control. Okay, now from PyTorch 1.12, you can actually access the utilization from your code. So I'm not sure what are the usages of this, but it's possible. So you can just access this code line, and it will give you the percent of time. So basically, the utilization percentage is just like we saw it in the nvidia-smi command. Okay, so another tip is cleaning the CUDA cache. So if you want to manually free up memory in the GPU, it sometimes helps to clean the cache stored in the GPU by calling torch.cuda.empty cache. And this is useful especially if you're working in a Jupyter notebook. So each time you run a cell, then some memory is occupied on the GPU. Of course, especially if you have like multiple models, or you send some tensors to the GPU and forgot about them, then you can actually call this line and it will free up memory. It is also useful to call this line after an epoch ends, and it will clean up some unnecessary tensors. But just keep in mind that you need to use this carefully, and so make sure you don't break your code by calling this line. But it's sometimes helpful, so try it and see if it works for you. Okay. So now is a list of general tips of good practices when you code in PyTorch. And we've covered most of them in the previous tutorials, but it's good to reiterate some stuff. Okay, so the first tip is, of course, always define the device automatically at the head of your code, at the top of your code, right? So we want our code to be agnostic to the type of acceleration. So this is why we use this automatic line and we put it at the top of our code. So this means that we don't need to call the .to operation on a specific device, and it's just agnostic, so it can run on any device. Okay. Now here is another tip. So some operations, some PyTorch models, they have a field called inPlace. Okay, and inPlace, if you set it to true, then it performs the operation in place. It means that it's not creating a copy of the tensor. So it can save a little bit of memory, okay? So it's by default, it's false, but keep in mind that sometimes you can actually save a little bit of memory by using inPlace equals true. Now, it's not available for all models. It's mostly available for activations, but not all of them as well. So for ReLU, we have the inPlace operator, but you need to see if the activation supports that property. Okay. Now we can also, when we initialize a model and we call the .to device, we can actually iterate over the parameters and see that they are actually sitting on the correct device. So you can see here that the parameters of the model are sitting on the GPU. Good. Okay. Another thing to keep in mind when we code is to avoid unnecessary CPU-GPU synchronization. Now, we want to let the CPU run ahead of the accelerator, the GPU, as much as possible to make sure that the accelerator's work queue contains many operations. So if you want to utilize the GPU better, then do not call operations that require it to go back to the CPU. Okay, so for example, here are a couple of operations that actually require CPU-GPU synchronization. That means that we have to stop what we're doing and go back to the CPU. So for example, printing a tensor that sits on the GPU. And for example, of course, calling .cpu or operations like counting all the non-zeros or something and things like that. These operations require us to stop the queue and go back to the CPU. Okay, so you want to avoid you want to call these operations after you are done working on the or processing your GPU workload. So, for example, this you will call this at the end of an epoch and not in the middle. Okay. Okay. Another good tip is when you create or initialize new tensors for reasons that are not so when you initialize tensors that are not weights or parameters that are automatically created on the device, you want to keep in mind that when you create a new tensor, it is usually initialized on the CPU, and then if you want to perform operations on the GPU, then you need to transfer it to the GPU. But you can actually initialize the tensor directly on the GPU. And here is how it works. So generally you would do this, right? And then you would set it into the device. And this means that you initialize it on the CPU and send it to the GPU. But you can actually create it directly on the GPU. Okay, so this is the good practice. So keep that in mind. So it can also save a little bit of time, especially if you create a lot of tensors. Okay. Now, specifically for accelerating our code using a GPU, then we have the CUDA drivers, right? And we have when we use convolutional neural networks, right? So the convolution operation or the convolution layer, right? It can be performed using multiple algorithms. Now, PyTorch supports many of them, and you should pick the algorithm that performs better, of course, and is faster. Now, the way it picks the way PyTorch picks the correct algorithm is usually by running a short benchmark at the beginning of your code, and selects the kernel that provides the best performance for your current hardware. Okay. Now the way we enable this, so we need to call the cuDNN.benchmark equals true before the training loop, right? And before the model starts training, then it will pick the fastest convolution algorithm, though this is true for CNNs. Okay. Now here are a couple of things to note. The auto-tuner decisions may be non-deterministic, so different algorithm may be selected for different runs, and in some rare cases, it's better to run convolution networks with auto-tuner disabled to avoid the overhead associated with algorithm selection for each input size. Now, if you care about reproducibility, so that means getting similar results for each run, or as similar as possible, then you should turn it off. Okay, and you should also turn on or activate the deterministic operation. It doesn't mean that the result will be the same, but it will be as similar as possible. Okay, so keep that in mind, that these two lines are required for reproducibility. Okay. Another tip is disabling the gradient calculation for validation or inference. So we've talked about this. So basically, because of autograd, each time you perform a mathematical operation on a tensor and it requires a grad field is true, then a graph will be built in the memory, and of course we will save activations, and this will cause an increase in memory. Now, when we do validation, we don't care about the gradients at this point. So the way we do it is wrapping our code with the wrapper, with the decorator, with torch.noGrad, and this means that operations on gradients will not be tracked and will not be saved on memory, and this is because we don't need gradients, and this will be faster and will save memory. So keep that in mind. Now we also want to turn off operations that change their behavior at train time and at inference time. So for example, dropout or batch normalization, right? But after you are done, make sure to get them back to the train mode. Okay. Okay. Another tip, so it's specific for convolutional neural networks with batch normalization. So usually when you initialize the conv2d layer, then the bias field is equals true. So by default, we add a bias parameter, right? But if you are using, if your layer is followed by a batch normalization, then the bias is not needed because there is a bias that is added from the batch norm. So basically you don't need it, and you can save time. Okay, and so the reason batch norm is we don't need to use bias before batch norm is because we subtract the mean, and it effectively cancels out the effect of the bias. So and there is so batch norm has a shift and bias parameters. So basically you can it will use this one. Okay, so it will save some time. Okay, so keep that in mind. Okay, now another tip which can lead to a very minor performance gain. So instead of calling optimizer.zeroGrad to zero out the gradients, we can actually set the gradients instead of 0 to none. Now, why is this different? So 0 is a number, and number is using bits, right? And it occupies memory. Now, instead, if you use none, then it means that nothing is used. Okay, so basically you don't use memory. So you can save a little bit of memory, and of course make things faster by setting them to none. Okay, now note that it's usually it's kind of risky. Okay, so only do this. So try it, see if it works and doesn't lead to any errors, right? But there are reasons why you should be careful, and here are some examples. So when you try to access a gradient and perform some manual operation on it, and then If you used set to none equals true, then this value will be none, and then perhaps an error will be thrown that you cannot perform the operation you wanted on a non value, right? Now, and another thing is that if your backward pass, if during your backpropagation there are parameters that are not updated, then they will stay none, right? And then it can cause problems because their field will be known, and so it can lead to some issues. Okay, and this is also true when some optimizers actually treat zeros and none differently. So keep that in mind, that you are not destroying something by setting to none. So just see if it works and does not raise any errors, and if it does not, then go ahead, use it. Okay. Another tip is when we use pre-trained models, then usually we don't care about, we have no intention of changing their weights, right? So of course, for fine tuning we need to change their weights, but if we only need to use them as, for example, as score givers. So basically there are networks that can give us some score, and the input to these networks are trainable parameters. So we want to save memory, and we don't want PyTorch to compute gradients for these weights, the weights of the pre-trained models. So two examples for this would be perceptual loss. So basically we're training a pre-trained vision model, a VGG network, and we use the output of the layers as the loss function. So of course we want to propagate gradients through these layers, but we don't care about the gradients of these layers. We just want it for the backpropagation, right? So we don't want to store the gradients there, right? Another example is clip. So clip gives us a score for pairs of images and text, and we want to sometimes use this score as guidance for a generative network. So we need to propagate the gradients through the clip network, but we don't care about updating the clip network weight itself. Now, if we will wrap the entire operation with torch.no-grad, then no gradient will be tracked, even for the input. But we do care about the input to these networks. We want gradients for this input. So this is why what we do is just turn off the gradients of the model, and we do not use torch.no-grad. Okay. So here is an example. So for example, we initialize the VGG, right? And then we just turn off its gradient, but we can still propagate gradient through the VGG network, right? So if we want to input an image to or an output of a network to the VGG network, we can still calculate the gradients because we did not wrap it with torch.no-grad. Okay. Now a general tip is, of course, avoid for loops. I guess this is nothing new. And of course it can save us many time, and we want to do operations in parallel and batch everything as much as we can. Now the simplest approach is just just stacking everything on the batch dimension. So this means everything can happen in parallel. And for example, if we have a tensor like this, then we can just stack everything on the first dimension and do everything in parallel, right? Now, there are times when we cannot avoid for loops. This is reasonable, but it's worth spending time seeing if you can batch things and not use for loops. Okay, so this is just general good practice, which is true not only for neural networks. Okay, another thing which is kind of new is from Torch 2.0, it's possible to compile models for speedup gate on certain GPU architectures, so mostly the newer GPU architectures, so H100, A100, or even V100. So this is available on Google Colab. Now the way it works is it makes the PyTorch code run faster by just-in-time compiling, or JIT, into optimized kernels, and I'll talk about it a bit more in the second part. But and the idea is that instead of instead of calling many operations, we can just call much less operations by fusing operators. Now I'll show you what it means in a minute, but basically it means that we can speed up the kernel, speed up the GPU utilization by less calling for kernels. So okay, so how it works? So you do everything the same, right? And after you are initializing your model, you are compiling it. Okay. Now there are several modes for compiling. So the default one is a preset that tries to compile efficiently without taking too long to compile or using extra memory. So this is the default mode. But there are other modes which may take longer time to compile, but when you train your model, it will be faster eventually. So for example, reduce overhead reduces the framework overhead by a lot more, but causes the small amount of extra memory. Max autotune compiles, takes longer to compile, but it will give you the fastest code it can generate, right? So you can click here for more information on modes, right? But then after you are done compiling, everything is the same. So for example, you can even compile a pre-trained model. Okay, so and after you are done compiling, everything is the same, right? So all your training and everything is the same. Okay, now one thing to note here is the torch.compile currently only works on Linux machines. So if you try to run torch.compile on Windows, it will throw an error that it can't do it. Okay, so just keep that in mind. Okay, now a bit more about the JIT compiling. Then the idea is that if we have multiple mathematical operations, and of course it should be run on the GPU, then each operation is a kernel. And here you can see we have multiplication, summation, division. And what we can do is we can actually bake everything to a single kernel. And the way we do this is as follows. We take our element-wise operation or function, and we just add this decorator. And then PyTorch will compile it, and this will lead to less calls for kernels. Okay, and this is called kernel fusing, right? So it usually works better for element-wise or point-wise operations, right? And most of the functions in PyTorch, in native PyTorch. So if you call torch.syn, then it's already compiled for you. You don't need to compile it yourself. Sorry, to fuse it yourself, not compile, fuse it. Okay. Okay, great. So usually activations, RNN cells, things like that works really well. And of course, the main speedups will be for newer architecture. So JIT works really good on newer GPU architectures. Okay, now we shift our focus to talk about a bit on data loading. And this can be a serious bottleneck when we're training our models. So we usually work with large data sets, and there is a lot of overhead when we transfer the data from the CPU to the GPU and even storing the data on our memory. And we will discuss how we can make things faster. And usually when you follow these tips that I'll give you in a minute, you'll see major speedups, and it's independent of your GPU architecture, right? It's just how you handle the data. Okay, so the idea is that the data loading process itself can be lengthy. So for example, the data itself is complex, or you are doing a lot of pre-processing before you work on this data. And this can result in a lot of CPU time while the GPU sits idle, right? So you will see that you have low GPU utilization. So we would like to fetch the data as fast as possible, and of course, and quickly transfer it to the GPU. And there are a couple of approaches to achieve this. I'll cover some of them, but of course, if you want to dive deeper, then go on the PyTorch website and you can see more tips. Okay, so the first thing is that is using pin memory and data loading. Okay, so pin memory is used to speed up a CPU to GPU memory copy operations. So when you do tensor.to CUDA, right? By ensuring that none of the memory that is to be copied is on the disk, okay? So there is a diagram here that tries to give you an idea of what pin memory is doing. But the idea is that we can simply use it in PyTorch by using pin memory equals true in our data loader, right? And usually it helps in speeding up. I have a table below, but sometimes it's not really doing, sometimes it's not really helping too much. So just try with and without and see if it works for you, right? And the reason it sometimes does not work is that it requires that the operation system is willing to give PyTorch process as much main memory as it needs to complete its load and transfer operations, okay? So, so the idea of caching pin memory is useful, and it's very simple to use. Okay. Another thing is which is super critical and works, and usually even works better than pin memory, and of course you can combine them, is using multiple workers to load the data, right? So if you are you have a multi-core GPU, right? And you want several workers, several processes to fetch the data, right? So we can easily do this by inputting num workers greater than 0 to the data loader. Now, what is the number that is the best fit here? So you need to play with it, but there is a general rule that the num workers should be 4 times your number of GPUs. And this is highly machine dependent, and you should treat it as a hyperparameter, right? So I would start with 4 or 8. So modern computers have multi-core CPUs. So 4 or 8 are good numbers. Now there are a couple of ways to search for this number. So we can see here a great discussion on how to search for it, but there is also a nice tool script that you can run once and see what is the optimal number of workers by the time, and then just use it for the rest of your code, right? So there are a couple of notes before you use it. So having more workers will increase the memory usage, of course. And num workers equals 0 means that the main process will do the data loading when needed. And num workers equals 1 is the same as any number, but you will have one single worker, which is probably slower. So this is why there is a difference between 0 and 1, because 1 will still initialize a new process, while 0 will just use the main process. So here are here's a small benchmark. Okay, so first of all, you can use both of them, bit memory and num workers. Now here's a small benchmark here that you can see the effect of num workers and pin memory. Okay, so we can see that the best times are around 4 workers and pin memory equals true. So this is a very good baseline to start with, and then you can start playing with the parameters. In this case, for example, going to 8 led to an increase. Okay, so just start with 4 with pin memory equals true, and pin memory should only be true for when you train on the GPU. Okay, num workers is true for CPU as well, but pin memory is only required for GPU training. Right. Another training tip, so we covered this in the CNN tutorial. So any operation that can be done on the GPU should be done on the GPU. Okay, so for example, data augmentations is a popular example where we do a lot of pre-processing on the CPU, and we can make things faster and do it on a batch with Cornea. So Cornea will also help us get differentiable augmentations, but mainly it operates on tensors, so everything is faster. And we saw this table where we we saved a lot of time by just performing the augmentation on the batch and not on each data separately with Torch Vision. Right. Okay. So a couple of more training tips. So when we're training large models and we work with a lot of data, then training can take a lot of time. But we still have a couple of approaches to speed up the training. This is what is done today with the large models. So the big companies, they utilize this kind of approaches in one way or another, and we will cover them. And just know that it's a whole new world. These techniques. So keep that in mind, and if you want to dive deeper, then feel free, and there is a lot of information available. Okay. So the two main approaches I'm going to discuss is the first one is automatic mix precision, or AMP. Instead of working with tensor at full precision, so float 32, we can sometimes work at half precision for float 16, and sometimes even use lower precision, so we can just use 8 bits and things like that. So keep that in mind. There is a new development in this field, especially with large language models, where we quantize everything, and we get a lot of performance gains, speed up from using low precision. And the second approach, and of course these two can be combined, is distributed training. So instead, if you have machines with more than one GPU, then we can actually distribute the training over more than one GPU, and this will lead to increased batch size, of course, and faster processing, faster training. So let's begin with mixed precision and AMP. The idea is that, so let's begin with why, okay? So in this graph here, you can see that when we use AMP, automatic mixed precision, so basically this means that when possible, PyTorch works in float 16, so not it works at half precision. Then we can get speedups, major speedups, especially with large models and all types, so CNNs, transformers, everything. So we can see that there are large gains, especially when we work with newer architectures, okay? And the idea is that the automatic mixed precision technique, it will, so you don't need to think about it too much, you just use the recipe, and PyTorch will handle all the transfer between the precisions, and then you can get similar performance, but at greater speed. So we covered this in more detail in the AMP tutorial, but there is a general recipe. So this code basically covers everything you need to know for most of your projects. The idea is that we're going to use two things. The first one is a gradient scaler. So gradient scaling helps us prevent gradients with small magnitude from flashing to zero. So this is called underflowing when training with mixed precision. So this is the first component, and the second component is the autocast component. Okay, so let's see what happens. So what lines in the training group are new? So the first thing is a scaler. Okay, so the scaler will be used if we use AMP. And our training loop is changed as follows. So before we wrap the forward pass with autocast, and autocast will perform any operation that PyTorch can in float 16, and otherwise it will resort to full precision, but you don't need to think about it. PyTorch will handle it for you. Okay, and we calculate the loss, right? Now, this is everything that is wrapped with the autocast, right? Outside the autocast, we do the regular stuff, so zero grad, backward, and step. So it's important that the backward pass happens outside the autocast. Keep that in mind. Okay, so how it works. So we zero grad, just like we always do. We can also set to none, okay? Then we scale the loss. Okay, we use our gradient scaler, and it will help us avoid the underflowing. And then over that, we do the backward. Okay, now the optimizer step, then it's using the scaler. Okay, so the scaler needs to come and it needs to be used also for the backward and also for the step. Okay, and finally we update the scaler state. You can read about this gradient scaling a bit more, but this is the general recipe. Not much has changed. Okay, but it can lead to major speedups, especially on your architectures. Okay, now the second thing is distributed training. Now, there are many ways to do distributed training, especially with PyTorch, but I'm going to recommend the simplest one and the one I like the most, which is HuggingFace Accelerate. Now, HuggingFace Accelerate is a wrapper for PyTorch distributed, which is the distributed training code. And it makes everything much more simple, and there are minimal changes, and basically all you need to do is tell Accelerate how many GPUs you have, okay, and how many CPU cores you want to use, and it will take care of the rest. Okay, so run pip install Accelerate, and this is and these are the new lines that are added to your code. So you initialize an accelerator module, right? Instance of accelerator. Then you need to prepare after you initialize everything, so your model, data, and everything. You use Accelerator to prepare the model, optimizer, and data. So basically, it will distribute everything on the GPUs. And then the only difference in the training loop is that instead of calling loss.backwards, you call accelerator.backward with the losses input. That's all. Now, if you have more than one GPU, then just run this line and tell accelerator that you want 4 GPUs or 2 GPUs or whatever, how many number you have. And the code runs the same, but much, much faster. And if you'll take a look at how at the original torch.distributed library, it's a lot of boilerplate code, and you don't want to mess around with it, especially if you want fast results. So Accelerator is the best way to do this currently. Okay, right. Great. So another thing that can help us monitor our code is the PyTorch Profiler, and it is a great tool to determine the most expensive operators in the model and analyze the execution time. So you see that you train your models and you see that an epoch takes some time, and you want to understand which operation was the most expensive one, which operation takes the most of the memory, which operation takes a lot of the GPU utilization. So basically the PyTorch profiler is super simple to use, and you can analyze your model with it. So here's an example of how we use it. So we have a ResNet here. Now we want to profile the utilization or the operations on the CPU, right? So we can actually use the profiler and see what happens during the forward pass. So you can see what operations are cost us the most. And you can sort it by the time, right? But you can also sort it by the memory. Okay, so the memory, right? All right. So here, sorry, here we are still sorting by time. I just want to show you that we can also track the shape, okay? But we can also sort by memory right here. So we can see which operation took the most of the memory. So not surprisingly, batch norm is quite costly. Great. And we can also analyze the GPU, okay? So we can also profile our model on the GPU. So we can sort by the CUDA total time. So we will see here, so we jump to the second row because there is not enough space, but you can see the costly operations on the GPU. So a really nice tool to debug your model, to understand which operation takes the most time, and maybe you can optimize it better, maybe use JIT fusion, or maybe use AMP and things like that. Great. Okay. So that's about it with the general tips. Now I'm going to end with a couple of notes on reinforcement learning. So in the deep learning course, we don't deal with reinforcement learning, but some of you are doing reinforcement learning, and I want to tell you about a couple of stuff that can help us do RL a bit faster. Now, in online RL, the main bottleneck is the interaction with your environment in order to collect data, which usually occurs in a simulated environment and runs on the CPU. So you have a video game, for example, Atari, and you want to train a model on Atari, but you want to train a model to solve Atari or to play some games from Atari, but the simulator itself runs on the CPU. So before we need to collect data online. As we improve, we need to collect new data. So we stopped our training and go to the data collection phase, and this happens on the CPU. So the GPU sits idle for a long time. And what you'll see is that when you print nvidia-smi, you can see spikes in the GPU utility. So sometimes it's 90% and sometimes it's 10%. Okay. Now, there are several approaches to speed up the RL process. So for example, one can utilize simulators that natively run on GPUs, where the input and outputs are already tensors, right? And this can reduce the CPU-GPU latency. And of course, everything that runs on the GPU is faster. So we need to wait for a shorter time. And another perspective is just, okay, we can't run it on the GPU, but let's utilize the CPU multi-processing. So just utilizing several environments in parallel, which will hopefully reduce the CPU time. So let's first talk about GPU-based simulators. There are not many of them. So we have Isaac's Gyms by NVIDIA. So not surprisingly, the GPU company also works on GPU accelerated simulators. So Isaac's Gym is quite popular today, and it has support in many libraries, and just means that we can do a lot of or collect data from many environments in parallel, and everything is on the GPU, so it's super fast. Another simulation is Google's Brax, and this makes, and in addition to being run on the GPU, it is also differentiable. It's a differentiable physics engine, so you actually can propagate gradients through the simulation, which is something very rare today, and not many simulations are making this possible. Now, I'll just note that Mujoko, which is also a popular simulator, is a new version, and they actively work on making it work on the GPU. So keep that in mind. Now, as for other accelerations possible, so when you can't run your simulation on the GPU, then you can maybe parallel or batch environments on the CPU using multiprocessing. So one way to do this is with nfpool. So nfpool can utilize a lot of cores, CPU cores, and have a lot of environments in parallel. And it's a great solution for when you can't run your simulation on the GPU, right? And you can see here that we can get major speedups using this nfpool approach. And it supports many frameworks. So if you work in CleanRL, then you can use nfpool and train a lot faster, because you can collect data a lot faster. Another approach. So basically today we have a lot of libraries for reinforcement learning, and there are a couple of popular ones. So the most popular one I would say is stable baselines. It has a set of reliable implementation of our algorithm in PyTorch. And basically it supports Isaac's Gym and nfpool and everything that we talked about. And this is what people usually use, because stable baselines, as the name stands, means that we have baselines for many algorithms. So if you want to implement something better, we have a good baseline to see if we actually improve anything. Another popular RL library is Elegant RL. So it's very similar to stable baselines in its idea, and according to its authors, it's much more stable than stable baseline 3, and there are a couple of techniques to achieve that. And it also supports Isaac's Gym and vectorized environments. So we can see a comparison with stable baseline 3. Now, finally. So this is a very recent. The PyTorch team has established a reinforcement learning sub-library. So like we have Torch Vision and Torch Audio and Torch Text, we are going to have Torch RL. So we are still at the beginning, but you can already use it. So Torch RL is available, and you can see there are official tutorials for this on the PyTorch website. And basically, hopefully, everything that comes from PyTorch will be faster. So keep that in mind. If you want to work with native PyTorch, then it's also possible. Okay, so this was a bag of tips and tricks for better utilization. I hope you will find this helpful, and if you follow these guidelines, you are guaranteed to have some speedups and hopefully some gains in performance as well. Okay, so thank you for watching.